Okay guys, week 2 of GEO Friday. Here we are, it's Thursday night and I am racing to try to get this thing done, and you are holding me accountable, and I like that about you. Okay, so today we're going to talk about some groundwater basics and dive a little bit into aquifers. Now, the whole topic of aquifers is really huge, so we're just going to brush the surface today and then we're going to get a little bit more in depth next week. So there's a couple big picture things we need to keep in mind when we think about water and the water cycle. So the first thing is that water is always moving around the planet, and it's moving at completely different rates depending on what form the water is in. So think about like a rain cloud moving across the plains and precipitation in that rain cloud and how fast it moves and then falls to the ground, versus maybe like a glacier that takes thousands of years and gets locked up in an ice sheet and then takes a few more thousand years to melt. So surface water flow is obviously anything that we can see on the surface. So things like lakes, streams, rivers, canals, reservoirs, the obvious stuff. Groundwater is a little bit sneakier. It's actually bound up within the pore spaces and cracks inside of solid rock hidden underground. So the water that we're going to be focusing on in this series is ultimately groundwater, and that's because over 88% of people in our state of Nebraska drink groundwater, so it's hugely important to protect it. So groundwater is widespread across the world, but that doesn't necessarily mean that it's easily accessible. Accessibility depends on a couple of things, namely porosity and permeability. I had an idea for visualizing permeability and porosity when I was cutting sweet potatoes for dinner the other night. Check it out. So porosity is the percentage of space in a rock, sediment, or soil that is void. Permeability is the interconnectedness of the porosity in a rock, or in other words, the ability of a porous rock, sediment, or soil to transmit a fluid. When we talk about permeability with regard to water, it's also referred to as hydraulic conductivity. The porosity and permeability of rocks and sediments depend completely on the processes that deposited those materials. So let's take a look at a river, for example. So up high in the mountains, rivers move pretty fast due to the steep grade, and then they can transport huge rocks. As the grade levels out, down on the plains, the water velocity slows and the river can only move smaller sediments like sands and gravels. And as the river nears the shore, it's moving very slowly and deposits the finest, lightest sediments on the delta fan. Since the size of sediments that rivers move is dictated by the water velocity, it makes them pretty good organizers of sediment. Let's imagine that these sweet potato slices are grains of sand in a river deposit. All of the grains are roughly the same size and shape, and there are big gaps between them, meaning this deposit has a high porosity. Now, if we space the grains out a little bit, the pore spaces are connected to one another, providing higher permeability, or hydraulic conductivity. Water can move fairly well through this kind of deposit, which makes sandstones deposited by river channels good homes for groundwater. These sediments are known as being well sorted. Now let's take a different kind of depositional environment, like a glacial system. Unlike rivers, glaciers aren't very good at organizing sediment. As they advance, they rip up sediment and rocks and jumble them up like a big, slow conveyor belt moving down a glacial valley. When the glacier begins to melt and retreat, it deposits the jumbled sediments known as glacial till. Now, there are exceptions to every rule, but generally speaking, till isn't a very good home for groundwater because all the smaller grains can fill in the spaces between bigger grains, which gives till a lower porosity and permeability. These sediments are poorly sorted. It takes water a long time to get through a glacial till deposit, or the deposit acts as a barrier altogether. So thinking about our permeability and porosity experiment with sweet potatoes, we know that not all sediments are appropriate or good homes for groundwater. So the sediments that are bad homes for groundwater are known as confining layers, and these act as layers that water moves very slowly through or not at all through. And then the sediments that are good homes for groundwater are known as aquifers. So next week, we're going to dive even deeper into the different kinds of aquifers that we can find across our state. And this is really cool because on the surface, Nebraska seems flat and relatively geologically uneventful. However, when you look in the subsurface, you'll find that there's a whole slew of different geologic settings ranging from glaciers to volcanic deposits to shallow seaways to riverbeds. And then we're going to look at some well construction, and then we're going to look at what pumping groundwater does to the overall water table. We'll see you next time. Relative